Have you ever wondered how engineers can predict the exact path of a satellite? Or, how a robot arm can pull off a complex task with just perfect precision? Well, it all comes down to a set of fundamental principles, kind of like the hidden rules of motion. Okay, let's dive in and uncover the blueprint that governs pretty much everything that moves. So, the big question we're tackling here is this. How do we take something that's incredibly complicated, with all its moving parts and all the forces acting on it, and then build a mathematical model that can actually predict what it's going to do next? It sounds like a huge challenge, but the approach, it's surprisingly elegant.
Just look at this airplane. To us, it's one object, right? But in dynamics, it's a system. You've got inputs, things like thrust from the engines, lift from the wings, and you get outputs, which is, well, the plane's movement. Now, to understand this, we can't analyze every single atom. We need a simpler way to look at it.
And that brings us to the first absolutely crucial step in all of engineering and physics. Before you can predict anything, you have to simplify reality. You have to turn it into a model you can actually work with.
This is the golden rule, really. We create an abstraction, a stand-in for the real thing. It's not about being perfectly accurate in every tiny detail. Nope, it's about capturing the essence of the motion we actually care about.
So how do we simplify? Well, we generally use one of these three models: the particle, the rigid body, or the deformable body. You can think of them as different levels of zoom. For today, we're going to focus on the first two, because they are the most fundamental. So let's break them down.
The simplest model of all is the particle. This is where we shrink an entire object, like our huge airplane, down to a single dot in space. And this is perfect if all you care about is where the plane is going. Say, you're tracking its flight path from New York to LA. We just ignore its size, its shape, and we definitely ignore its rotation. But what if you're the pilot? You definitely care about rotation. And that's where the rigid body model comes in. Here, the object has a shape and size, but we make one really key assumption. It doesn't bend or stretch or deform at all. It can move and it can spin, but the distance between any 2 points on it is always constant. This thing is the real workhorse of dynamics.
And this quote just illustrates the point perfectly. The same object can be modeled differently depending on the question you're asking. For a flight controller who's just tracking dots on a screen, yeah, the plane is a particle. But for the pilot who's totally concerned with its attitude, its orientation in space, like its roll, pitch, and yaw, for them that plane is absolutely a rigid body.
Okay, so once we've picked our model, the next step is to figure out its menu of possible movements. How many independent ways can this object actually move? This brings us to another core concept. It's called degrees of freedom, or DOFs for short. It's basically just a count. It's the number of independent dials you would need to turn to put an object in any possible position and orientation. It's the number of ways it's free to move. So, for a free-floating rigid body out there in space, think of the International Space Station. What's that magic number? It's 6.
So why 6? Well, think about it. It can move along 3 different axes, up and down, left and right, forward and backward. That's 3 what we call translations. And it can also rotate around each of those 3 axes, what we call roll, pitch, and yaw. That's 3 rotations. So 3 plus 3 equals 6 degrees of freedom.
This slide actually breaks it down nicely. In a simpler 2D world, on a flat surface, a little particle can only move left/right and forward/backward. That's 2 degrees of freedom. But a rigid body on that same surface, it can do all that, plus it can spin, and that rotation gives it a 3rd degree of freedom.
So an object floating in space has all this freedom, but down here on Earth, things are rarely that free, are they? They're connected to stuff, they're on tracks, they're held in place. These are the rules of the game, and in dynamics, we call them constraints.
Let's see how this works with something we see every single day. A door. A door is a rigid body. If it were just floating in space, it would have those 6 degrees of freedom, but it's attached to a frame by a hinge. So how does that simple little hinge change things?
That little hinge is a master of control. It completely stops the door from moving up, down, or sideways. Bam, that's 3 translations gone. It also stops it from tilting forward or twisting side to side. That's 2 rotations gone. It applies 5 distinct constraints.
So here's the punchline. We started with 6 degrees of freedom. The hinge introduced 5 constraints. And what are we left with? Just one. The single, predictable rotation of the door swinging open and closed. See? Constraints are what make the world predictable.
All right, let's take all of these ideas, rigid bodies, degrees of freedom, and constraints, and apply them to a more complex case study, one that reveals a pretty fascinating paradox.
The common car. Now, on a flat plane, we know a rigid body has 3 degrees of freedom. But the wheels on a car add some very specific rules, or constraints, about how it's allowed to move. Let's see what they are.
And here's the paradox. The wheels create a constraint. A car can't instantly just slide sideways. Its velocity at any given moment is restricted. And yet, through a series of forward, backward, and turning motions, just think about parallel parking, it can end up in any position with any orientation on that plane. So, its velocity is limited, but its final position isn't. How is that possible?
The solution has a kind of tricky name. It's called a non-halonomic constraint, but really it's just a fancy term for a super cool idea. It's a rule that limits your velocity, how you can move right now, but it doesn't limit your final position or where you can eventually get to. This is the secret sauce that makes parallel parking and all sorts of complex robot navigation possible.
So, why do we care about any of this? Because these simple building blocks, simplifying systems, counting their freedom, and defining their limits, they form the fundamental blueprint for understanding and predicting motion.
Let's recap the whole thing. First, we model reality by simplifying a complex object into a system, like a particle or a rigid body. Second, we count its potential for movement using degrees of freedom. Third, we define the real-world rules of the game using constraints. You put those 3 together, and that's how you get the power to predict the outcome.
And this brings us to a final thought. From a bicycle turning a corner to the wild way a spinning top stays upright, these rules are operating all around us. Now that you can see this blueprint, what everyday object do you look at and think, wow, the physics behind that is way more complex than I ever imagined?